Hello everyone. Today we will discuss the some very basic concepts used in the digital communication systems, and these are Gaussian distribution, central limit theorem, and Gaussian noise. Now I will start with what is a Gaussian distribution. Now, if you take a random variable capital X, so this curve shows the probability density function of this random variable, and how it is expressed as P subscript capital X, which is the random variable, and argument is X. So X is along the x-axis, horizontal axis. This is the equation of this probability density function, and it is given by 1 over 2 pi sigma square exponent minus x minus mu whole square divided by 2 sigma square. Now it is a bell-shaped curve because the probability density function looks like the shape of the cross section of a bell. So if you look at the cross section of a bell, so this curve will give a feeling that it is a bell-shaped curve. So that is why it is very commonly used as a bell-shaped curve also. Gaussian distribution is called as the bell-shaped curve. Now this equation 1 is the equation for the PDF probability density function. Mu, if you look at this equation, there are two parameters, mu and sigma. So mu and sigma are variables, and it turns out that mu is the mean of this PDF and sigma is the standard deviation. So therefore sigma square will be the variance. Sigma indicates the width of this curve. So mu is the mean and sigma will indicate the width of the curve, the value of sigma. Mu and sigma are two parameters which change the shape of the this bell-shaped curve. Now, why is Gaussian distribution so famous? So it is used very much used for general statistical analysis, but actually, if you look at straight away the application of this Gaussian distribution, I mean, it may not fit in certain examples. Like for example, if you look at the marks of students in a class, the marks of students are scaled according to the bell curve or according to the Gaussian distribution. Students tend to get marks in a class distributed. If you plot the histograms of their marks, and you will observe that some will tend to get lower marks and some will get high marks. Maximum will get near average. But this Gaussian distribution is not the exact function to use in this case because this function is continuous and marks are discrete. The random variable, which is in this present case is the marks of the students, so it's a discrete random variable. And also if you look at this curve goes from minus infinity to infinity. That means it has got negative values also. So this function is continuous and it is not best suited graph for explaining the marks of students in a class. There can be some more discrete random variable examples like people's height, age in a demography. So they all are discrete random variables, and these values will be positive. So if you try to fit in these random variables with this function, it may not be very well suited to give an impression of the distribution. So the question is that why is that Gaussian distribution is used then? So it leads to what is called the central limit theorem, which is the core fundamental of using this Gaussian distribution so commonly. Now this theorem says that any number of random variables, if they have the same distribution and if you add them up, if any number of random variables are there and if they have the same distribution and if you add them up, then the overall distribution will be a Gaussian distribution irrespective of individual distributions, right? Now if you have two random variables like n and m, so in a receiver in an electronic receivers or any electronic circuitry, so there will be different parts of the circuit. So maybe some amplifier is there, oscillators are there, and there are many more components can be present in this circuit. So as you this noise is basically, I'm taking the example of two random variables, but there will be many more random variables in a receiver in receiver electronics. Now when you switch on the receiver, the electrons, the material will heat up, and the Brownian motion of electrons in the various amplifiers will be represented by these random variables. Now if you add all these random variables, then this all will add up to Gaussian distribution, right? I will come to the Gaussian noise in the coming slides, but before coming to the Gaussian noise, let me formally explain what is central limit theorem. Now, central limit theorem says that if you have many random variables, so I am expressing those random variables as x1, x2 up to xn. So there are n number of random variables, let's say. Now, if all random variables are taken from same distribution, so that means they have the same probability distribution. If these are independent, if these random variables are independent, and if they have the same mean and variance, then uh, then if you add all the random variables, that means sigma uh, k going from 1 to n, this random variable values, and if you subtract the mean values, right? So and divide by the square root of the number, add all, if you add all the random variables minus their mean, right, divide by the square root of the number, then you get a new random variable, which is this y, right? So central limit theorem says that under weak conditions, the probability density function of y is Gaussian as n approaches infinity with mean 0. Why mean 0? Because you are subtracting mean from every random variable value, and sigma square as the variance, right? So this is what I was trying to explain here, that why the central limit theorem explains that Gaussian distribution is so famous in digital communication systems. Now let us look at what is Gaussian noise. Now to explain the concept of Gaussian noise, let me take this xk. What is x? X is a set here of 0 comma 1. That means either 0 can be transmitted from the transmitter side or 1 can be transmitted, right? At so k, index k, the subscript here k is the time. So transmitted symbol, so xk is the transmitted symbol, either 1 or 0 at time k. So 1 can be represented by, let's say, voltage, 5 volts can be used to represent 1, and no voltage can be represented as 0. Now these pulse shapes, or these bits in the form of these pulse shapes, will be passed on to the channel. So at the receiver end, you will see that you will have to amplify the signal. You will have to put an amplifier here. Then you will have to use a correlator or a matched filter here. And then after that, you need to sample at every capital T seconds. Then you get yk, which is the received signal. So the overall system can be expressed in this with this equation: yk equal to h xk. Xk is of course the transmitted symbol. So h is the attenuation during the channel, and yk is the received sampled version of the received signal. Now this complete receiver needs electronics. So this all will be done. This all the functionality will be done using electronics, and needs to turn on when you. So that's what I was trying to explain in the previous slide also. So you need to turn on this electronics using a power supply, and when you turn on using power supply, all electronics will heat up, and electrons will start moving due to heat in various parts. So we don't simply receive H, which is the attenuation, but also noise due to this receiver electronics. So it turns out that it is additive, and it turns out that the noise is additive and random. So therefore yk is hxk plus nk, so which is additive white Gaussian noise. And if you apply the central limit theorem, as I was trying to explain in the previous slides, that the noise present in various parts of the electronics, they all act as independent random variables. Now, if you add them up using the central limit theorem, the overall distribution will overall noise distribution will be Gaussian distribution, and it also turns out that it is additive. So that's why we say this noise as the additive white Gaussian noise. White means, I will come to that. So if you try to plot if you plot yk and do many measurements, so if you try to do many measurements of this received signal, right? So it will be a Gaussian distribution. Independent at all k, noise is independent at all times, at all k, and identically distributed. That means same distribution with same shape. So at any pair of times, the values are identically distributed of noise components and statistically independent. And that's why we say that the noise components are uncorrelated, because every noise component at every point of time is identically distributed and statistically independent. So there is no correlation between the noise components, and we say that the noise is uncorrelated, and of course it will have the Gaussian distribution. Thank you for this very basic lecture, which is the concepts are used in digital communication. Thank you very much.